Okay, I think we're on.
Excellent. Hello, everyone, and welcome to today's webinar, What's So Phenomenal About Phenomena? I'm glad you took time out of your very busy day to join us today. My name is Heath Williams. I'm the marketing manager for Amplify Science, and I'm joined today by Rebecca Abbott. She's the professional development lead at the Learning Design Group at UC Berkeley's Lawrence Hall of Science. You've probably heard of phenomena-based instruction. It's probably why you're here today. And Rebecca is going to walk us through what that actually means and how it's embodied in an NGSS design curriculum. Before I hand it over to Rebecca, a couple of quick housekeeping notes. You're going to be on mute for the duration of this webinar, but we do want to hear from you. You'll notice a Q&A button on the bottom of your screen. Drop any questions you have as we go in that window, and we'll be sure to leave some time for questions at the end of the session. This webinar is also going to be recorded. You'll receive an email tomorrow with a link to the recording to watch on demand or to share with colleagues who may not have been able to make it today. All right, with that, let's get started. I'm going to hand it over to Rebecca.
Okay, great. Well, happy to be here. Thank you, Heath, for the introduction. And thank you for those of you joining today. Like Heath mentioned, there's been a lot of talk about phenomena in the next generation science standards. And so I'm happy to be here with you today to dig in and tell you about more what that means. All right, so let's jump in. The focus of today's presentation will be to showcase the approach that we've developed to phenomenon-based teaching and learning as part of Amplify Science. As many of you likely know, the Lawrence Hall of Science and us at the Learning Design Group here have been in the work of developing this program, phenomenon-based instruction, to meet the needs of NGSS for the last number of years, and have partnered in a deep collaboration with Amplify in order to bring phenomenon-based teaching and learning to the classrooms across the country. So while we're going to be using examples from our program, Amplify Science, that we've developed together, those will mostly be just in terms of an exemplar, because the goal here is really to focus on what a phenomenon-based teaching and learning can look like, not really to focus in on the curriculum itself. So the plan for the session is we're going to spend some time thinking about a phenomena-based teaching and learning, phenomenon-based approach to teaching and learning, and just go through starting with what this means and moving on to why this is a powerful approach. And then with our 5th grade exemplar, we're going to show how it can look in a classroom. Now, just a note too, we've often done this in a hands-on way with a big group of participants and can't really have you do that as much. So as much as we can, we might have you participate, put in some ideas into that questions box that I'll respond to, and I'll also be showcasing one of our simulations somewhere along the way, so you can gather some evidence and respond back to some of the things that you're noticing and some of your observations. So stay tuned for those opportunities to participate. Okay, so as we get started, scientific phenomena. These are, of course, phenomena are observed. Now, this is actually a great place for you to go ahead and chat in your responses. As you're looking at that list of topics, and as you're looking at that list of phenomena, what do you notice? What jumps out at you as the difference between the two? So go ahead and type those into the Q&A chat box. And I'll wait just a moment for people to put in a couple of answers, and then I'll read them off. Okay, so a couple of folks who are quick are saying things like, well, the phenomena are more specific circumstances, like something you notice in a specific place and time. The phenomenon are also a real world, things that could actually really happen. Topics are more of sort of a content, right, wrong types of answers. People are saying topics are passive and phenomena are more action-oriented. And I've heard some people say too, topics not so motivating, that there's something that, we are doing because we're doing it in school, but not necessarily motivating in terms of getting kids' interest and engagement. Okay, great. Thank you so much for those responses. That was very fast. Okay, so we're going to keep going. And so what we're going to take a look at next is, what does that look like in a curriculum? So it's something that we think about a lot as curriculum developers, but how do units of instruction, how are they different depending on if they're organized around a topic versus when they're organized around a phenomenon? And like many of you said a moment ago, if the topics themselves lend themselves to facts or memorizing or having discrete knowledge related to topics, they're going to be things like let's discover or all about or what is it? Whereas phenomena, on the other hand, really lend themselves to why and how questions. And so you can see on the right-hand column, some of those phenomena that we had a moment ago are now sort of in a question form, where we ask these what caused or how or why types of questions. And these are the kinds of questions that scientists ask. So it really mirrors that same authentic way that scientists wonder about the world. So the NGSS call the main phenomena that guides a unit or instructional sequence the anchoring or anchor phenomena. And it's called this because an entire unit is about figuring out this phenomena. An anchor phenomena invites students to ask how or why something works. It needs to be rich and complex. So it motivates the learning and the investigations for an entire instructional unit. And an anchoring phenomena is specific to one event or location, like some of you said when you were noticing that a moment ago. It's not general. So for instance, when we asked what caused the storms in Galetown to become more severe, we weren't asking just what causes storms in general to become more severe. So now that we've had an opportunity to think a little bit about what the difference between topic-based and phenomena-based approach might be, I'd like for you to think about the shift to a phenomena-based approach. What do you think the advantages are? Go ahead and chat that response next into the questions box. And this is just a question about, based on that left-hand column and the right-hand column, what are the advantages of using a phenomena-based approach? And I'll check in the questions box. Okay, so someone brought up again that it says that you can start to participate in what scientists do every day for their research. It lets them see what scientists do every day for their research. Other folks are saying that it's about the process of science, that there's not like sort of a finite answer. More relevant, having students actually work on an issue. These are all really great comments from our participants. Provoking student questions increases student ownership and motivation. Yeah, these are all fantastic reasons why we would move towards a phenomenon-based approach, the real life aspect of it. And so in the end, we think about this as that scientists don't wonder about topics, this authentic approach that a lot of you brought up. It's that we put ourselves into the role of a scientist. Scientists don't wonder about the water cycle, they wonder about phenomena. Why is something happening? And science is about figuring things out. You can't figure out a topic, you can figure out a phenomenon. It's through this process of figuring out phenomena that scientists and students can be versed in a topic area. So if we want students to engage in learning about the natural world as scientists do, then we want to afford them the opportunities to construct their knowledge in ways that scientists do. So in other words, focusing instruction on phenomena that students are motivated to explain shifts the focus from just learning about to figuring out. This idea of figuring out is one of the most significant shifts of NGSS as we move from learning a list of discrete facts to involving yourself in the process of figuring out. So phenomenon helps us do that, but so does three-dimensional learning. I'm not sure that it's even possible to do three-dimensional learning without a phenomena to figure out. So these two really go hand in hand, where 3D learning is a structure that helps support students make that shift from learning about to figuring out as they use scientific and engineering practices and as they apply cross-cutting concepts to figure out the core ideas. So again, if science is all about figuring things out and you can't figure out a topic, that we engage in figuring out a phenomena using all three dimensions, just like a scientist might. So we're going to go on to the how. So this is the part where we're going to see, well, how do we do this? How does phenomenon-based teaching and learning look like in the classroom? Many people have delved into designing units around phenomena, and there are a number of approaches that could get them there, and I wanted to showcase the way that we've conceived of guiding students along the path to be able to figure out phenomena and through that process gain the deep conceptual understanding related to it. Okay, so what we're going to do is we're going to jump into an exemplar from one of our 5th grade units. It's called The Earth System, Investigating Water Shortages. And what I'm going to showcase in this unit will help you gain some insight into all of Amplify Science units, all the way from kindergarten through 8th grade, the units we've designed, and how we've constructed units so that students figure out phenomena. So in this particular unit, students take on the role of water resource engineers, and what they're tasked to do is figure out what's happening on an island called Ferris Island. So specifically, you can see in the image here, one side of Ferris Island is experiencing a water shortage, and the other side is not. And so even though Ferris is a fictional island, many of us live in areas that they can relate to some of this, but it's based on real-world locations. So just a reminder, this is what's called the anchor phenomena. This is something that sustains the learning over a long number of lessons, in this case 26 lessons, which could last 4 or 5 weeks. And it has to do with the fact that one side of the island, East Ferris, is having a water shortage, and West Ferris is not. So the question form of that anchor phenomena is, why is East Ferris experiencing the water shortage? What's going on this island? All right, so in our units, what we do is we tend to break up the learning into different sequences that we call chapters. This unit this image shows that the 5 chapters that go into this unit. You can see that there's the larger question. Well, there has been this larger question overall. Why is East Ferris experiencing a water shortage? It's broken up into 5 smaller questions, and each of them is associated with a chapter of the unit. So we explain to students that when scientists tackle big questions, they break the larger question into smaller questions. And what we're going to do in our little mini experience today is only dive into just the front end of the unit. So we're just going to take a peek at chapter 1, just really to define the problem. What's the issue with why East Ferris is running out of water while West Ferris is not? And then we're also going to take a peek of into chapter 2, where we talk about an investigation question that the students tackle. And so hopefully this will provide a picture of not just what phenomenon-based instruction can look like, but what it looks like to have the students be doing the figuring out. Okay, so let's jump into chapter 1. The question that we start off with is why is East Ferris running out of water while West Ferris is not? And this helps students focus on further defining the problem, which those of you savvy with NGSS know that this is part of science and engineering practice number 1, where we're asking questions and defining problems, and namely investigating, well, why is this happening? Why is East Ferris running out of water while West Ferris is not? So we have a number of lessons, and they're scaffolded, where students use a number of different materials, and we're not going to get to use them, but just so you know, they use a reference book called the Water Encyclopedia. They get some support in reading graphs, and they test some things out in a hands-on way. So here's one of the graphs that they take a look at both on a slide and also in a book that they're accessing. It says basically in a graph called Places Where Water Exists on Earth, we ask students, what does this graph show? And many of them, like you're noticing now, notice that, well, wait a minute, most of the water is salt water in the ocean, and salt water is unusable for most human purposes. There's very little water that is fresh. And this helps us sort of conceive of that idea that, oh wait, when we're talking about a water shortage, we're really talking about this fresh water shortage. And also helps dispel a preconception that students have, like, wait a minute, there's living on an island. They are surrounded by water. How could there be a water shortage when there's so much water? So we kind of define that idea of what is salt water, what is fresh water, and what are we talking about. Okay, so the next thing they take a look at, well, where is the fresh water on Earth? Well, students are asked, or they ask, think about, well, what does this graph show, and how does that help us? What it shows is that fresh water is mostly in glaciers and in underground and groundwater, and a very small amount of it is actually surface fresh water and available for human use. And it's an opportunity here to introduce the concept of the hydrosphere. And so, of course, groundwater, there's a preconception that often happens here where there's like a giant underground lake somewhere. And so this is where students can do an actual hands-on investigation with the water percolating through, but thinking about how there are, there's no one large place where groundwater is stored. The ground and rocks below us might seem solid, but of course there are tiny cracks in the rock and spaces between the rock that water can seep into. So when you add up all of those water in those tiny spaces, it actually amounts to a lot of the water on Earth. So now we've got a hydrosphere and a geosphere connection. Okay, so take a look at this data that I have on the screen here. Students are told that the mayor of East Ferris sent us some data on the amount of rain that each city has gotten over time. So as we're trying to figure this out, I want you to go ahead and chat in the questions box here. What do you think this data shows? We've got rainfall in East Ferris. We've got rainfall in West Ferris. I'll go ahead and check the questions box here. But yeah, so folks are saying there's more rainfall in the West. That's pretty clear from just the numbers. And is there any moments when it seems like there's a complete drought? Is there anywhere that it's completely fallen off, or is it pretty steady, pretty consistent in both areas, as one of our participants is saying? Okay, perfect. So that's what the kids notice as well. There's no evidence of a drought. What would the data look like if there were a drought is that one year would be way lower than some of the others, but it looks pretty, both in East, it's consistent throughout, and in the West, more or less. So again, why is there a water shortage? No drought. Interesting. So they go on to synthesize the information about rainfall, but then also get some other information from the mayor about the population on the island, which is that it's increasing. So we ask students, why would that matter for water usage? But the bottom line becomes, after we investigate some of these graphs and understand what the mayor is showing us, is that East Ferris is using more water than it's collecting. And it rains more in West Ferris. They don't experience the water shortage that East Ferris is experiencing. They can have some reserves. Okay, so that's, we didn't go through the whole experience, but that was essentially defining the problem in chapter 1. There's more rainfall, population is growth is in both areas, but that means that they're just using more water in East Ferris than they can replenish. On to chapter 2 then. Why? Why is there more rain over West Ferris than East Ferris? What's going on with that? Why does that happen? Okay, so then the students spend a number of lessons thinking about breaking up this is a big question, so we break it up into even smaller questions. And so we call these investigation questions, and as part of figuring out why more rain forms over West Ferris than East Ferris, we ask 3 investigation questions that take us a day or 2 each to investigate. Well, how do drops of water form? How do raindrops form up in the atmosphere? And finally, thinking about where does water vapor in the air come from? We do not show all these investigation questions at once. So for example, because it kind of gives away some of the answer by the end. So we wait for students to figure things out before we introduce the next investigation question. Okay, so at the beginning of chapter 2, all students are doing is figuring out what they want to work on is how do drops of water form? So this is a fun one where we have to figure out where students do a combination of doing and talking and reading, and I'm just going to tell you how it happens basically. So in this case, what we do is the teacher challenges the students to make drops of water appear on the outside of a cup of water. And it's a pretty open-ended investigation the kids can do. They get cups, they get ice, they get thermometers, they can get some salt, and they investigate for basically trying to think about how can they create this phenomenon. They pay close attention to what factors seem to be important. Is it the material that the cup is made out of? Is it a temperature thing? Is it an ingredients thing? And then they observe closely and get some data. So once they've done that, they figure out the water drops form on a cup when the cup is cold. So it has to do with temperature, and that's an important sort of thing that they've just figured out. It has to do with temperature. And then that's fine. The water drops form on the outside of a cup of water, but where do the drops of water come from? Because we say, we're trying to figure out, why this is happening. And this is always this is a tricky one because students are challenged to think about a couple different possibilities that they come in thinking. So often students think that the drops might come from the water inside of the cup, and other students might have an idea that the drops come from the air outside of the cup or around the cup. So they get to investigate this for a little bit, and what they do is they have some. This can either be guided by the teacher, or students can come up with more investigations. But they can observe on that top picture, you see a cold, empty cup from the freezer. As that comes down to room temperature, the water drops still form on the outside of the cup, even though it had no water in it. So that sort of debunks the idea that there has to be water inside of the cup to come out. And then we do another investigation. This one works pretty well, especially if it's humid. But basically, if you have Ziploc bags, you put one cup where you remove the air around the cup, and you notice that the cold cup that's sitting on the countertop does get condensation on it, whereas the cup inside the Ziploc bag does not. Okay, so students know a little bit more now about where those droplets come from. And of course, they start to get introduced to, or start to hear the word, or start to use the word condensation, and talk about that in more of a concrete way at this point. So what is in the air that becomes water? How could I get a Ziploc and get rid of the air and there's no water? So we have to investigate that. Students search for evidence in a book called The Water Encyclopedia. They take a closer look at what air is comprised of. The air that surrounds the Earth is called the atmosphere, and how the atmosphere is another sphere or another system as part of the Earth's systems. And we find out that indeed there is air in the atmosphere that includes other gases such as water vapor. And so that helps us figure a lot of things out in terms of there is water in gas form in the air. And so with all of these different types of evidence that students are gathering, we know that water drops form on a cup when it's cold. We know that the water drops on the cup do not come from the water inside the cup. They seem to come from the air. And then they figure out that there is water vapor in the air, and that has us thinking that the water drops that form on a cup come from the air around the cup. So that fits with the evidence that we gathered that some drops of water form on the cup, etc. So as we try to answer our investigation question, how do drops of water form? We're thinking drops of water can form when enough water vapor gets cold and condenses into liquid water. So for fifth graders, this is not told to them. This takes them multiple lessons to figure out. All right, so remember that we call these smaller questions that help us answer the chapter question, we call them investigation questions. These investigation questions actually help students figure out what are called investigative phenomena. The investigation questions, of course, are the question form of the investigative phenomena. So I'm going to show you real quick then is a graphic to show sort of how we went through that sequence just now. So we'll zoom in more closely. What we started off with was an anchor phenomena, and then that broke down into thinking about a smaller piece of the puzzle, the investigative phenomenon. And after introducing that and wondering about it, students gather evidence from different sources, and that leads to the construction of and understanding of new science ideas. Those new science ideas in turn help students make sense of that anchor phenomenon. But it starts to make sense. They're not quite finished yet. So in this particular case, I'll just let you take a peek at this slide here, but this is essentially what we did. We noticed something happening, drops of water forming on the outside of a cup of water. We did our investigation. We came up with a new key concept, and we partially started answering the idea of East Ferris is experiencing a water shortage. But this shows that really all this new science idea would do is lead us to have to investigate more. And then again, to investigate more until we had a more complete understanding of what's happening with that anchor phenomenon. So we could call that investigating sub-phenomenon, or investigating, parts of the anchor phenomenon, and so forth. The new science ideas that they get along those gray boxes at the bottom helps get them closer and closer to figuring out the anchor phenomenon. Okay, so let's keep track of where we are here. We're trying to figure out why East Ferris is experiencing a water shortage. We know that there is more rain that falls over West Ferris than East Ferris because we saw the rainfall data. Now we're working to figure out why more rain forms over East Ferris and West Ferris. Now that we know how drops of water form, what about how that will help us figure out, well, how do raindrops form? So here we go. We're trying to figure out how raindrops form. This is the next investigative phenomenon. So now, since we can't go up to the sky to observe, we're going to use a computer simulation to investigate how raindrops form. We call it a simulation. So I'm going to go ahead and pop over to my simulation here. I'm going to choose a landscape, different landscape. And these, what I'll just say quickly, oh, let me pause that. Let me start over here. So in our units, we have simulations in every single unit, starting in grade 4, and other digital tools for the grades 2 and 3. And this one is the one that we use for this particular unit, and the students use it multiple times to do different investigations. So I'm going to go ahead and let it play as I keep talking. And basically, you're going to start to see something happening in landscape 3. And go ahead and type in any observations in the Q&A. All right, so I'll go ahead and check my Q&A box and see if anyone's making any observations. All right, so I see in the Q&A box, I pressed pause for a second. Clouds are forming and rising, and it's raining. And on the west side, it is raining on the west side, that's true. All right, so I'm gonna start this over. And what we're gonna do then is I am gonna turn on the molecules, which you got a sneak peek at. And so you'll see now, and by the way, on the right-hand corner here, you can see the liquid and the vapor is indicated. You get a different view of it. And keep your observations coming if you're interested in typing them in. Just someone said, that's cool. Well, that's exactly what the kids say. And they just get to play with this, of course, the first time they use it. And then as they go throughout the unit, they use it for more and more specific investigations. So again, here, we're trying to think about, how do raindrops form? So one tool we can use, if you can see on the top left corner, I'm going to click on this pulsing dot here. It's called the Analyze button. And what we can do is we can replay what we just saw happening. So I'm going to back it up, not to make you dizzy, and I'll restart it. So I'm scrubbing, using the scrubber below to sort of slow it down and see what's happening. Because remember, how does rain form? We're taking a look here. Well, I can see what's happening with molecules coming together. Oh, and there's the moment when rain forms, huh? So let me take a look here. What I can do is I can, and if you can see now on my right-hand side of my screen, that's my zoom in window. So I just got to notice my internet connection was unstable. So let me know if I get cut off here. Hopefully we are connected. All right, so I'm going to pack up just a second and go forward, but hopefully you can start to see in that zoom in window, how at one point those raindrops start to fall. And so what students start to notice is that it's a quantity thing. When you get enough little clusters of what's the blue here, the water molecules clustering together, they do form and fall. They form together or connect together and they fall. So that gives us a clue in terms of if there's enough water coming together, it will fall as rain. And so folks are noticing the clouds, rain on the west side, and so forth. Okay, so let's go ahead and run it one more time. I'm going to restart my run. And this time I'm going to turn the wind on to the right. So you can watch what happens in sort of a typical evolving situation. So you can keep going with your observations here. So we're figuring out how rain forms. And yeah, someone is pointing out that there's something about a certain altitude or a certain height above the surface where that water is actually is turning from vapor to liquid when it reaches a certain altitude, not attitude. So what I'm noticing now too is that all the rain is forming on one side of the mountain, and those clouds are not carrying enough water vapor to fall on the other side of the mountain. Okay, and that's what one of our participants just said too. Once the clouds go over the mountain, there's no rain left since it went down on the other side. Pause it here. So really nice observation. So yeah, you can see, I mean, there's all kinds of other cool things going on that the kids get to investigate, but you can see it actually seeps back into groundwater. The other thing you can start to notice is you can sort of click on a single and analyze. You can click on a single water droplet like this and sort of trace its path and watch it go from liquid water and evaporate. So that whole idea of evaporation and condensation and condensing into clouds and so forth. So there's a lot of rich things to discover and figure out with this simulation. And this particular point in the unit, we only did a couple of them. So thanks for participating in that. I love that simulation too. A couple of people said, okay, I gotta get access to that and play with it, because I know it's hard to just watch me do it, and it's fun to play with yourself. Okay, so we're gonna keep going. So we're gathering evidence from the simulation about how raindrops form, and that I think we found out a lot of things from there. What we did to figure out how raindrops form is we changed variables and we observed processes from the simulation. They also look back into the water encyclopedia. They also do some more hands-on investigations, and they get these two key concepts: that raindrops can form when enough water vapor gets cold and condenses into liquid water, and water molecules are spread apart in water vapor, and water molecules get close together in liquid water. Okay, so here's an example of how we've broken down all of chapter 2. So in the first sequence of activities, you can see that we think about just how drops of water form at all by doing hands-on tests and observations. But that leads us to a new question. Well, what about raindrops? Will they form in the atmosphere? That's something to investigate. Well, let's get some evidence with that in a sim and in the water encyclopedia. And then it's the same for the third investigative phenomenon. Once we know that water molecules are closer together and raindrops form from water vapor, what we do is we need to know, well, how does water vapor get into the atmosphere in the first place? And so students do some evaporation experiments where they conduct investigations, both in the simulation and in a hands-on way, where you can see, well, you can't see the evaporation, but you can gather evidence of evaporation happening in a few different ways. So just to take a look at the structure then. Like anchor phenomena, these investigative phenomena and those phenomena, the investigative phenomena across the top layer, these also invite why and how questions. And they also invite students to get curious and wonder and set up investigations in which they discover important science ideas. An anchor phenomena is selected because explaining it will lead students to discover a wide swath of science content that the unit is meant to address. The scheme of phenomena-based learning is not new. This is something we've seen in other countries or in other eras of science reform in the past. But the NGSS features this approach, as well as the ideas of anchoring phenomena and investigative phenomena. And if you are using an NGSS aligned program or are designing units, these elements should be built into the curriculum. So here, let's just again juxtapose these two ways of doing science. The phenomenon-based example has a comparable topic-based example above and below. Reflect on the difference. Why does more rain form over East Ferris than West Ferris? They do that, they figure that out based on observable phenomena. The observable phenomena include the drops of water form, that raindrops form. We could actually observe that in the simulation. Even though it's a model, it's something that we can observe and investigate. And in the case of where does water vapor come from, that third one, there's both a hands-on experience so they can observe evidence of the phenomenon at the macro level and then engage with the simulation at the nano level. So we're giving students these investigative phenomena are concrete observable things that they can go on to explain. As opposed, of course, to the topic-based, where it's just finding out what is evaporation. And even if there is an investigation that could help students know that, there is often an element of telling that would have to happen, and that telling would happen in the case of in the form of a textbook, or maybe a lecture, or maybe even a video of some kind. But that topic-based telling doesn't work for all students. What we're seeing is that the phenomenon-based really puts the students at the center of the investigation. So I really want to thank you for your participation. We do have time for some Q&A at the end here. And so I'm going to go ahead and open up my questions box for a moment. And again, feel free to contact me or Heath, of course, who you're in contact with now via this webinar. And if you want more information or would like to get an opportunity to try out or demo, get any demos from this unit at all.
Yeah. One quick plug, we did have someone say in here, I seriously need to get access to this program. If you go to amplify.com/science/sample, you can access 2 sample units, one from grades K5 and one from grades 6-8, so you can poke around and experience this for yourself. Any questions?
I see someone raising their hand. I'm not sure if I know how to. There we go. Okay, so I got one question. If you're the person who raised your hand, go ahead and type your answer in the Q&A box. I don't think I know how to answer the hand raise.
Yeah, that's a feature I'm not familiar with either.
Sorry about that. Anyway, but Victoria asked a question. Any advice for first-year teachers teaching elementary science? Oh, yes. I have a lot of advice in terms of teaching. We have, first of all, just, get to know the program as a whole. We have a lot of advice on some of our other webinars, for example, on internalizing the program. If you have elementary science with Amplify Science, which I don't know if you're asking that, but if you're a first-year teacher teaching Amplify Science, I would really encourage, team approach in terms of getting folks together and really getting to know the unit resources and getting to know the program as a whole, and just, and trusting that the elements for you to teach are there. I think many teachers are used to going outside of a program and finding and creating their own curriculum materials, but even just by following the program itself, you're learning NGSS, you're learning hands-on, you're learning investigating with phenomenon as you teach and learn. So you're learning alongside the kids. So that would be my advice for if you're implementing for the very first time.
Morella asked to say that address for the sample site one more time. It's amplify.com/science/sample. And if anyone didn't catch that, just shoot me an email after the webinar and I can email you directly.
Okay, then we have a question about simulations in terms of accessibility. And so there's different, so we do get questions about accessibility in terms of being adaptable for different site-enabled folks. And unfortunately, at this point, there is one color palette for students to use the simulations. That said, we surround these simulations with a lot of other activities. It's not a curriculum where it's like, okay, do this simulation and you should know everything. As you can see, we are gathering evidence from multiple sources. So the differentiation we offer for students is more in the form of teacher support and facilitation and multiple opportunities to gather evidence in different ways. So yes, they would need support with the colors, specifically a colorblind person, for example, to see the 2 different colors, but there's also the shapes, so things like that have been thought through when you're designing simulations. Okay, at this point, I'm not seeing any other questions.
Yeah, thank you so much to everyone for taking time out of your very busy days to join us for today's session. Like I mentioned when we started, you'll receive a link to the recording of today's webinar in your inbox tomorrow to watch on demand or share with your colleagues. So be on the lookout for that. Have a great rest of your day, and thanks for joining.